After the ship's dry docking, we noticed issues with this temperature control valve.
Problema ngayon, nag-overshoot eh. Tinignan ko sa baba, bigla pumasok, bigla sarap.
We will go back in time.
We're reviewing GMR playback from post-docking dates, then comparing with pre-docking data when the system ran smoothly. Think of GMR as the engine room's black box. You can go back in time and see what actually happened. This feature of the integrated automation system helps us gather facts and reduce assumptions in our ProbeGnosis. This three-way rotary valve controls main engine high temperature, cooling water, heat recovery. Let's look at 31st August 2025. That is 6 days after completion of docking in Poland. Now, many factors can affect this valve's behavior, even with the same PID. One major factor is the renewal of C-valves, including the MEHT cooling lines. The new valve flaps had different profiles from the old ones. Slight fluid dynamics changes, cascading effects.
Tinignan ko yung hunting trending noong August 31. After dry dock na nakita natin yung problema.
Now, let's analyze the controller trend.
Punta na tayo ng Finland. August 31. Hindi niya makuha yung set point. Masunod.
The problem, the loop overshoots and fails to settle on the set point.
Hello number. 7.77. Measured value.
Measured value shows output temperature after the three-way mixing valve. Persistent oscillation appears, and valve dampening never settles throughout the cycle. In PID terms, the loop is hunting. This case is not covered in the troubleshooting manual. The complete cycle, overshoot, sudden close, reopen, and continuous oscillation throughout valve movement. In auto mode, it cannot catch up with the set point of 77 degrees Celsius in a stable way.
Label to manual. Engineers put to manual. Cannot catch up.
The duty engineers switch to manual. They increase valve opening from 57% to 62% to 70% to pull more flow from the cooler side. Fast forward to the 6th of September. The trend shows the same unstable pattern. Now let's compare post-docking to pre-docking for the same event. The PID values are the same. This is the temperature control valve trending when it was running clean.
Ito yung setting niya nung July 28.
Yan yung setting.
4:15:15.
Because it's when review this problem.
Ito yung ngayon.
Meanwhile, here's the real-time value of the same valve. The main engine is stopped and the three-way rotary valve is at 90% bypass. Our initial plan was to replace the actuator motor. But first, we will check fundamentals, actuator response, and the feedback loop.
Fast forward natin ang before dry dock.
Yan yung before dry dock.
Di ba, mga August 4.
This work can be done with the main engine secure, so we do not disrupt the sailing schedule.
Pag may shop, sabihin na andar yung engine. Yan, naka-andar yung freshwater generator.
Then August 4.
Naka-andar yung freshwater generator. Papakap yung ano yan, kaya nag-drop. Nag-time mo lang.
Nag-drop dito.
Nag-slow down yan. Tapos napasok yung freshwater generator.
Join me as we investigate the cause of this problem.
Kailangan natin may investigat ano nangyayari.
Let's probe it on.
I saw the name immediately. I knew this is the guy. Again.
See you next time, mate.
Sige,
Good
thank you
luck.
very much.
Bye.
This is our second probe of this three-way temperature control valve on this vessel. Same valve behavior, but we're looking deeper this time. First probe was 10th September 2023, almost 2 years ago. If you'd like to see what we probed back then, check the show notes. This time, we're taking a different ProbeGnostic approach, and with better evaluated experience than before, tackling components we didn't address in the previous investigation. Notice the valve's local indicator, 100% bypass, fully closed position. Here's our actuator motor. And motor capacitor, ready for replacement if needed. But first, we'll verify if the installed units actually require replacement. To check the capacitor, I set the multimeter to capacitance mode. For accurate measurement, the lead wires must be removed from the capacitor. The installed unit, rated at 5 microfarads, now measures only 3.62 microfarads. That's well below its tolerance range of 4.75 to 5.5 microfarads. It's failing, and it hints we need to renew it right away. but the spare capacitors we have on board are both 6 microfarads. Now, what happens in this case? When capacitance drops like this from 5 to 3.6, the actuator motor loses torque, starts weaker, and responds slower. That sluggish response shows up in the control loop as overshoot, oscillation, or hunting. Replacing it with 6 microfarads restores stronger torque and faster movement. It helps the actuator catch up with the set point, but since 6 microfarads is higher than the original spec, the motor may also draw slightly more current and run hotter. That's why it's important to monitor its running current and temperature after replacement to confirm it's within safe limits. In short, 3.6 microfarads actuator is weak and unstable. 6 microfarads actuator is stronger but must be tested. This is a practical fix, but the best long-term solution is always to use the exact spec capacitor. Safety first. When setting potentiometer resistance, always operate with actuator power off, otherwise ohmmeter readings will be inaccurate. So, first step, isolate the 220 volt AC supply to the 3-way rotary valve actuator. Now, let's engage first our mind before our hands.
We're looking for high tech. This one HD cooling. Play position, rail dust. With brightness.
We check for any voltage first before working on dead circuit. Since there is no potential, it's safe to proceed. Now, we check the motor and coupling. Disconnect its power connection. And remove it from mounting. The motor shaft rotates smoothly. And so does the valve coupling. Next, manually close the valve by pulling the lever and turning the wheel clockwise. This step is required before calibrating the potentiometer. With the close limit micro switch engaged by the cam. Here are the potentiometer terminals. Its job is to provide feedback. 0% closed, 100% open, or any position in between. We'll follow the steps for checking the potentiometer. But here's the challenge. The potentiometer leads are wired to the PCU card located behind the actuator. It's not easy to access. To illustrate, let's look at the LT cooling system actuator. Here you can see how the PCU card is mounted and where the potentiometer leads connect. Back to the HT cooling system actuator. Since we cannot access the PCU card directly, we'll improvise. By cutting the wire near the potentiometer and install a connector. This becomes our probing point. We'll probe the white, low value, and blue, common, leads. The as-found resistance is 0.896 kilo ohms, far above the ideal range of 80 to 120 ohms. Our goal is to set the value within 80 to 120 ohms when the valve is fully closed. Once the resistance is set, reinstall the gear and fixing screw. Remount the actuator motor. terminal board, and all connections. Finally, put back the cover.
May pabalik naman. May pagka-erratic sir yung potentiometer.
Pero ngayon, maganda na yung response niya. Kasi tingnan mo, nag-exacto na naman siya sa benta. Pag ilinigay ko siya sa 45, let's say 45 kaparehas niya, di ba? Lalaro agad siya. Chug! Pick up agad siya. Hindi yung dati mataas na, ayaw pa. Ngayon, tingnan mo. Ngayon, pag na-meet niya pa, nag-stable na siya, dahan-dahan siya magsasara. Ang mangyayari dito, magta-trial and error lang tayo dito sa derivative.
Ganito yung
Matagal na sakit yan, yung alam mo na yan, yung potentiometer na yan. Masyadong sensitive.
orderan natin.
Oo.
Ganito ang nangyayari dun sa habang nag-a-adjust ako. Ganito yung potentiometer natin. Tatlo yung leg. 1. Dito ako naglalagay ng probe. So, ito 0 to 1K kilo. So, nag-0 setting tayo. So, 1K. So, ang sabi sa manual, kapag 0 setting, around 80 to 120.
120 yung kanya. Ohms.
So, habang pinipihit ko yung potentiometer,
Nag-i-erratic siya, iba-iba yung reading na kinukuha niya.
nagja-jump siya.
Oo.
Tapos, may time na nasa gitna OL. Tapos, saka siya babalik ng 800, 900. So, yung time na nasa kalagitnaan na nag-OL siya, doon yung mag-a-alarm.
Okay. Parehas din dito ulit. Ito may sakit din eh. Ganito rin sakit niyan eh. Pagka sinagad nyo dun sa 70 sa pag umabot na siya ng 82, bigla siyang ma-overshoot, tirik to. Ganon din ang mangyayari.
Yun yung time na nawala ng feedback, nag-OL. Akala niya walang feedback. Kaya alarm siya.
Alarm siya. Ito hindi na eh. Hindi na mo Ilagay ko sa, let's say, 44.
Mami-minimize naman natin yung alarm kapag maganda yung fine-tuning ng PID or yung galaw ng valve ng gear, dahan-dahan lang.
Sana, ayan. Hindi siya basta-basta sasagad agad Yung 1 degree, hindi niya, hanggang 33 lang siya. Not unless kung tumataas pa. Yung dati, pag ganyan, isasagad niya muna. Pag sagad niyang ganyan, mahirap nang bumalik. Kaya nangyayari, nagiging pendulum na hanggang doon na nagluloko-loko yung graph.
Hunting na.
Kaya ang ginawa ko, mas magasabi ko maganda pa, manual to. Kahit na napupuyat ako, okay lang. Kasi mag-problema tayo sa kung ano. Ayan Nagkaroon siya ng kung ano. Halimbawa, ilagay ko sa 45 na to. Ang reaction niya, tingnan mo. Ang reaction niya, ibibigla niya ng kunti. Sandali, ayusin ko.
Oh.
Ngayon, pag after a couple of seconds, nag-stabilize na yung sensing ko niya, doon na siya, ayan na. Kaya lang dito, maglalaro tayo dito. Sabi nga sa GPT, i-zero mo lahat to. Pagka i-zero mo to, tingnan ko yan. Hindi rin magpapakalima, sabi niya. Start with all gains, KP, K1, K2. Increase KP until the system response quickly but starts to oscillate. Tapos add KI to eliminate steady state error but watch for increasing oscillations. Mag-a-add ka raw ng KI. Tapos add KD to reduce overshoot in oscillations. Para hindi siya na-overshoot na. Kaya lang, sa atin, variable kasi ito eh. Hindi natin makuha yung sudden, hindi ito yung tipong ganito eh. Paiba-iba eh, lalo na nag-iba yung si water temperature. O tingnan mo, stable na siya sa 26. Ngayon, ilalagay ko sa 47. Susundin niya yung deviation limit na 4. Na kailangan, hindi ako umabot sa 4 na deviation limit, sumagad. Kaya, action agad siya oh. Isasara kita agad. Ganun ang nagiging forma niya. Yung luma, isasabi ko sa'yo noon, madali siyang bumaba. Pag umangat, hirap na siya. Kaya ang nangyayari, naaabutan na siya. Ito naman, lumalamig na, nagbubukas pa siya ng konti, nagkakaroon pa ng momentum. Kaya nangyayari, pag bumaba ng konti, itataas niya ang tagal bago sumara. Kaya ang nangyayari, pag sara, naabutan na naman siya hanggang siya, wala na. Nataranta na. Ang magiging common problem nun, kung hindi natin iminanulawan, it's either masunog yung motor, kasi iinit yan dahil siyempre sige ang galaw.
Sige ang ikot. Nobserbahan ko rin kanina nung in-overhead ko yung lever.
May init yan. Kaya nga nakadalawa na kami niyan kasi yung luma, ganun din na nangyari. O tingnan mo, hindi, yan ang maganda niyan kasi hindi siya sumasagad-agad ng sara eh. Hinihintay niya muna kasi pag sinagad mo ng sara, yan nagkakaproblema eh. Kasi bigla kang iinit dahil sinara mo eh. Ito okay na to, masaya na ako rito. Tingnan mo, pag pinipti ko, halimbawa 44, ilagay ko sa 48. 4 degrees na yung division limit niya. Isasara niya na. Kailangan hindi ako abutan ng 4. Pag inabot ako ng 4 degrees, 4% na 4 degrees na lamang, isasara ko na to. Para hindi na ako abutan. Kaya pag ilinagay mo sa kutsi ng 48, sarado na siya. Hindi niya na paabutin yung division limit na 4.
Maximum na to ano? Ng bulb.
Yan na. Okay yan. Masaya na ako dyan sa 90. Hindi na siya kung dyan. Dati lang 89 na nga yan eh. Okay na yan. Sarado talaga yan. Kasi ito ang nangyayari kasi dito, doon tama. Yung potentiometer na yung binabato niya, yun ang may problema. Kung isisiro natin yan, baka magka-problema pa tayo sa potentiometer. Yun ang nagiging problema.
Kaya mayroong place dito na 82-120. Mahirap tong i-zero.
Mahirap zero yan. Kasi iniiwasan ko rin na mag-zero ng sagad. Kasi alam mo kung bakit, kung zero ng sagad. Minsan nag-i-stack up dyan eh. Maski yung mga cargo pumps, hindi yan nasisiro ng sagad. Oo, yung valvula niya nasisiro, pero yung sa kwan niya, hindi. Kailan to?
Ito yung manual. Illustration niya. Dahil hindi ko maabot itong card, yung PCU card, dito ako nagsukat ng multimeter.
Ito yung mabigat dito eh. Ito. Dito nagkakaproblema eh. Dito nagkakaproblema palagi. Kasi minsan, hindi naman ito narili sa line. Ang nangyayari, kunting clearance mo lang, almost 3% ang nawawala.
Diyan ako natatagalan kanina. Kunting pihit ko lang.
Kasi ang potentiometer na ito, mayroon ng alog. Hindi na siya yung matigas. Meron ng ganun. Pag ginanon mo, nagbabago yung value eh. Hindi na siya stable. Ayan o, tingnan mo. 3% sarado siya. Hindi na sa debutate para mamaya makalimutan. Pinahirapan din ako nito. Ilang beses din ako nagka-problema.
To Today we're departing Finland. Now we can finally put the HT cooling system 3-way valve automation to the real test. Full speed ahead means constant thermal load, the exact conditions where our PID hunting originally appeared. Static testing in port only tells part of the story. Once underway, the main engine produces dynamic sustained heat that truly challenges the temperature control system. This is where we'll see if replacing the capacitor and recalibrating the potentiometer solve the hunting issue, the ultimate validation of our probe.
Ito nag-9.7, tumaas na. Kailangan ito tumaas na rin para magkaroon na siya ng signal na magbukas. We want to evade this. If it goes 105, I think, then it will make a
High temp alarm.
down. You see the output is slowly opening up a bit.
Yeah.
Tama lang yung standard na bukas.
Yung recording nung August 31, overshooting siya agad dito.
Oo, hindi niya kasi mabagal eh. Magkakaroon siya ng sign wheel. Bali, lalo na pag pabalik na, pabukas na, tagal, hindi niya na nakakayanan. Kailangan hindi siya, ba, nakaset yan sa 75, kailangan hindi siya mag 70, 70.5 kasi alarm may deviation. Malaman natin yan kung nag-full speed siya na nag-constant na yung load. Makita natin kung paano yung laro.
For this section, we asked ChatGPT, what is the best way to fine-tune PID controller? With the current PID settings of 4.0, 15.0 seconds, and 15.0 seconds respectively. This is for the main engine, HT cooling temperature control valve with a set point of 78 degrees Celsius in auto mode. ChatGPT suggested 3 simple and safe tuning sets, each to be tested one at a time.
We make it balance for a while para wala sa magkabi.
Manual mo na.
We stabilized the temperature in manual, then switched to auto with set A and observed it for over 20 minutes. Set A, conservative/stable, recommended if you see oscillation or valve hunting. P equals 3.0, I equals 15, and D equals 2.
Kapag aggressive, we need a fast actuator.
Mabilis yung response. Ito, conservative to. Hindi corrupt. Just like Roman is conservative.
About.
Ano susunod? Susunod natin.
Set B, balanced, a good trade-off between speed and damping. P equals 4.5, I equals 12, and D equals 2.5. We tried this set as well for another 20 minutes.
Okay, that's my final color.
Itong setting na to, halos hindi ito naglalayo sa setting natin ng dati.
Makikita mo raw yung totoong result niya after 20 minutes eh.
Roll follow up. Follow up. Engine switch.
Yes, go ahead.
1125. Incrementally message. Engine switch to zero.
Okay ka, 1125 NFC passage, switching to zero.
Ito yung mabilis niyang hahabulin yung set point.
Set C, aggressive/fast tracking set point, only for systems that respond quickly with a fast actuator. P equals 6.0, I equals 8, and D equals 3. After stabilizing, we tested set C in auto mode. but based on the trend, this was not acceptable. So we tried another approach, this time with a more detailed prompt for better recommendations. Now it gets interesting. We refined our prompt to ChatGPT by uploading the valve specification sheet, specifically identifying it as three-way rotary mixing valve. This specificity changed everything. The updated numeric settings account for how the controller interprets valve authority and flow sensitivity. Rotary valves produce variable authority, requiring more conservative gains and longer integral times than linear valves. Here's the recommended settings. Set A, safe, conservative, first test, P equals 2.0, I equals 90, D equals 0, off. Rationale, long integral prevents wind-up in low authority regions. No derivative to avoid amplifying valve position noise. Set B, balanced, if A too slow with decent valve authority, P equals 3.0, I equals 45, D equals 0.5, optional, rationale. Stronger proportional action, cautious integral, small derivative only if process variable is clean and actuator feedback is stable. Set C, faster, only with confirmed good authority across range. P equals 4.0, I equals 20 to 30, D equals 1.0, trim down if noisy. Rationale, use only if you have measured mapping and actuator is quick with tight position control. Now, here's the stepwise test sequence we followed. 1. Set controller to manual and stabilize output temperature close to the set point. 2. Load set A, switch to auto, and allow 30 to 60 minutes for the loop to settle. 3. Do a small set point bump of +2 degrees Celsius, then log PV and OP for at least 30 to 60 minutes. 4. If PV is stable but returns too slowly, try set B. This time we load set B with these settings. P equals 3.0, I equals 45.0, and D equals 0. We ran the loop for more than 30 minutes. After 7 days of observation, system performance is satisfactory. The hunting behavior is eliminated. Problem solved. From a hunting temperature control valve after dry docking to checking the actuator capacitor, recalibrating the potentiometer, and fine-tuning the PID loop, we've seen how methodical steps bring real solutions. The takeaway is simple. Always start with the fundamentals, gather facts, and let the trend records guide your ProbeGnosis. After 7 days of stable operation, the system is finally back on track. This has been another real-world troubleshooting case. Thank you for joining me on this probe. Until next time, keep on probing.